I'm recording. Take it away. Okay. All right. Oh, this board is still in bad shape. Now, speaking of final, so a couple people, okay, 3 people have scheduled their oral final. Still plenty of room in this remaining time for the rest of you if you want to do that. Instead of the coding option. Okay.
Email you that?
That probably would be a good idea because that way you can keep track of all the times that people have gotten and then make sure that there aren't any conflicts. I've accidentally double booked people before.
I was
Let's say teamwork.
Makes the dream work. I mean,
Don't either.
I mean,
Jeez. Okay. Anyone else have an even corner line to put out there? No, because there isn't one.
someone
All right.
here could rickroll you.
Oh, God. Okay. So, now, even though we're going to only focus on like part of one section where I was left off last time, and then starting another one, which I don't expect, I'm only going to cover part of it. I can only cover part of it today, and then we'll leave the rest for Tuesday. What's nice about this selection of topics is that I think it does a good job of really capturing the essence of what numerical analysis is about in terms of coming up with practical algorithms for solving problems, in this case differential equations, and also how we can analyze these methods to make sure that they're going to work, to try to have some certainty about when they'll work or under what conditions. So it may be only a small cross section of just the material we covered in this course, let alone the whole field, but I think it's a very informative cross section. Now, before I jump into it, now that I've chewed up 10 minutes, the one thing I would like to do, so this is something I'm going to offer some bonus points on. So this will be worth up to 10 points on a homework assignment. So in other words, if you messed up a homework problem, but you do this, then you won't have to redo that problem. So what I'd like you to do is I handed out, and I think everybody should have this now. So I handed out this last time, and also to anyone who wasn't here last time, the updated syllabus, which is also posted on the main page in Canvas. And what you'll see on the first page and spilling over into the second are outcomes, student learning outcomes, or newfangled teaching jargon for you. And yes, this is for that teaching workshop that I go to every week and will go to for the very last time ever tomorrow. Yeah, I'm not sick of it. What?
Cake? Called the last time called cake? Last time drinking?
Oh, it should work that way. And thank you.
And the last time. Yeah, I'm bringing cake back up. I want cake.
Okay.
Really,
Well,
never noticed.
thank you for a reminder for our last time. Okay. What you can do is, this will be a good test of how well you either pay attention today or take notes today. What I'd like you to do is, afterwards, go through these outcomes and point out to me in what way did what I covered today relate to those outcomes? Like, which of those outcomes are related to what I present? So that way you try to connect this small amount of material I covered today, the whole scheme of things, to the overall goals for the class. So you can give that a whirl and Maybe
Is
some
that like
points.
in a paragraph form?
Yeah, and so it's something you could just email it to me, or you can, if you're about to turn in a homework, you can include it in that, and I'll just add it to that score. So, however you want to do it. Okay. Okay. All right. Now, to quickly recap. From last time, who is calling me? Stop it. Okay. All right. Multi-step methods for the initial value problem. Y prime is f of ty, and y at the initial time is equal to y naught. And any of these time-stepping methods that we see, one-step or multi-step, will compute solution values yn, which is an approximation of the exact solution at time tn, and tn is equal to the initial time plus a multiple of h. H is the time step. Okay. So what I'm going to do is, instead of going through recapping general multi-step methods, because that's kind of hard to digest, I'm just going to throw up a couple examples of multi-step methods, and I'm going to work with those in what I'll present today. So first example is an Adams -4. And how many step method? This is a two-step method. So a two-step method will use yn and yn minus 1. So it reaches back only one step in time to try to improve the accuracy of the solution. So I showed you the three-step method last time and showing you what the coefficients are. So I'll just go ahead and write them down in this case. So h over 2, 3, f of tn yn minus f of tn minus 1 yn minus 1. Now, going forward, I've used this notation before. I'll abbreviate this as fn, and this is fn minus 1. Okay. All right, so the thing is, this is something that only requires one new evaluation of f each time step, this one, whereas this would have been evaluated during the previous time step. And because it's a two-step method, and it is explicit, there's no need to solve anything for yn plus 1, because yn plus 1 only appears here. So you can just plug and chug on the right side, get the value on the left side. And it is second order accurate, order h squared error. Okay. So that's one example of a multi-step method. And then I need two methods for what I'm going to show you. So the other method will be an Adams Moulton two-step method. So that is implicit. And that method would be yn plus 1, yn plus, okay, h over 12. Okay. 5 f of tn plus 1, yn plus 1. So now you have yn plus 1 appearing on both sides of the equation. That's what makes it implicit. So you'd have to solve for it somehow. Okay. Plus 8 f of tn yn minus f of tn minus 1 yn minus Okay. So notice that Adams' Moulton method has three terms, three f values. So there will be three beta coefficients, but we still call it two-step because it only reaches back to time tn minus 1. So that's what determines what kind of method we call it, two-step, three-step, four-step. It's how far back in time you reach. So if you have explicit and implicit Adams methods with the same number of steps, the implicit method will have one term more. And because of that extra term, it's one extra degree of accuracy. So the error is order h cubed. All right. So now you can always use these methods individually. So the Adams-Bashforth would certainly be the easier one. The Adams-Moulton method, you'd have to use some iteration, like a fixed point iteration, to solve this equation for yn plus 1. But what I'm going to show you is a way to use an implicit method kind of like an explicit one for efficiency's sake. And the idea is you actually use two methods together. So that way you get some of the benefits of the implicit method without all the work involved. Because if you're going to use fixed-point iteration on this or something like that, or Newton's method to solve this equation and to get it to converge, that's a lot of extra work. So we'd like to cut back on that. And that's what leads to the concept of a predictor-corrector method. Okay. So what you do is I'm going to illustrate how a predictor-corrector method works using these two methods, but you could choose any two multi-step methods. One of them explicit and one implicit. So the idea, what the need for a predictor-corrector method is, you need one Adams-Bashforth method, and actually, you could use a non-Adams method. I've never really seen it done, so we'll just stick with Adams. So you need one Adams-Bashforth method. Its role is the predictor. And then we need one Adams-Moulton method. And its role is the corrector. Okay. So here's how it proceeds. There's actually 4 steps to it. One is predict, evaluate, 3 is correct, and number 4 is also evaluate. So people refer to this as PECE to keep track of the steps. Predict, evaluate, correct, evaluate. All right. So now write down what all 4 of those steps actually are. So the predictor method, there's a predict step. You just go ahead and use the Adams-Bashforth method. So at the output, we don't call it yn plus 1 because it's not our final value. It's an intermediate. It's our prediction. It's our. Think of it as like an initial guess. Okay, so here you use the Adams-Bashforth method, whichever one you've chosen. Okay. So that gets the ball rolling. The next thing we do is we go ahead and plug this new y value into our time derivative f. So fn plus 1, I'll call it fn plus 1 tilde, is equal to f at tn plus 1, y tilde n plus 1. So what we computed during the first step gets plugged into f. Okay. Still writing? All right. Now we use the Adams-Moulton method for correction, but what we do now is we use this implicit method as if it was an explicit one. By taking our f value from a previous step, and we just go ahead and plug that in to the implicit method. So we're not performing an iteration like we normally would if we're just using an implicit method by itself. So we're saving ourselves some work. Okay. All right. And now we have our value of yn plus 1. Now, it's not necessarily as accurate, a yn plus 1, as opposed to if we were to actually perform the iteration and solve this equation for yn plus 1. But it's going to be pretty dang close. And besides, there's going to be error from using this time-stepping method anyway, so we might not even want to go to the trouble of running this to convergence. The last thing to do is fn plus 1 is going to be needed for the next time step, where it will be known as fn. We have to update it using this new y value. So fn plus 1 is equal to f at tn plus 1. So notice, same t value, but now the new y value goes in. So that way we get a better approximation of a time derivative at time tn plus 1. And so the only reason we do this is to have the best information available for the next time step. So when we carry out the next time step and we go to the Adams-Bashforth method, this fn will be equal to this because the index moves up by 1. And that's it. That's the Predictor-Corrector method. So now we have some of the advantages of the implicit methods. Like we tend to be able to use larger time steps. They have a higher order of accuracy than a explicit method of the same number of steps, but without all the work involved. That the explicit method has helped us cut down on some of that. Okay. All right. Now, but I need to explain, actually, I might have my outline a little backwards, how well it works and why this works. In fact, how we can make it work even better. Okay, so if we use a predictor-corrector and we use a m-step predictor and a p-step corrector. So now in the example, both a predictor and a corrector were two-step methods. That's not required. You don't have to make them the same number of steps. So the error is equal to, from the predictor nth order accuracy from that, plus the corrector, the order of accuracy is order h to the p plus 1. So, in effect, well, whichever is the lower power of h, that's going to be the dominant error. So really it's going to be order h to the minimum of m and p plus 1. Okay. So in that case, you might as well choose the predictor to have more steps. Like, so actually, you'd want m and p plus 1 to be equal, ideally, which I did not do in this example, but so that we're not giving anything up. But here's one variation, and that is after the initial prediction and correction, you repeat steps 3 and 4. You take your your fn plus 1, you use that in your corrector again, and update yn plus 1. So basically, you're performing an iteration, a fixed point iteration. So in other words, yn plus 1, k plus 1, like an iteration, is equal to yn plus, so using the method from this example, just for convenience. So it'd be 5f tn plus 1 yn plus 1 k plus 8fn minus fn minus 1. So the old yn plus 1 gets plugged in here on the right side to produce the new yn plus 1 on the left side. And we just keep plugging it in, keep going, until we get some convergence. Now you can think of this whole right side as g of yn plus 1 iteration k from fixed point iteration, which you've just been dealing with in homework 5, I believe it was. Yes, homework 5. Now, when does fixed point iteration converge? What needs to be true of g to make that happen, as you dealt with on that homework? What? G prime. The derivative of g must be so g prime, though, if I make a generic function of y, most of these things in here are constants. Yn's a constant. Fn, f minus 1, they're all constants. So it's 5h over 12 partial of f with respect to y. So we need that to be less than 1 in absolute value. Well, you're free to choose h however you like. So if you know something about partial of f with respect to y, f is a given function, so you can figure that out, you can guarantee convergence just by choosing h to be sufficiently small. And then that fixed point iteration will work. Okay. And you already have a decent initial guess going into it from the prediction. So you don't have any real issue there. And if you do this, that means that the order of accuracy of the predictor doesn't matter anymore, because all the predictor did was furnish an initial guess. From this point on, it's all about what the corrector does. So for this variation, the error is determined solely by the corrector. And I just realized that was really awful notation on my part to use the letter P to refer to the order of refer to the number of steps in the corrector. I should have done that the other way around, but oh well. Okay, so so if you're willing to incur that extra work, then if a corrector happens to be higher order accuracy, then that's what the order of accuracy that will prevail. And even if that's only 1 degree greater, that can make a big difference. Like in the example I had, second order versus third order. Because think of it this way, you decrease h by a factor of 10, you're talking about the error decreasing by a factor of 100 for second order versus 1,000 for third order. And that can also save you a lot of work because you need fewer time steps when you have higher order accuracy. Because the error is still going to be so small. That's why between like Euler's method, first order, versus a fork method, fourth order Bronco cutout, fourth order, the number of time steps you would need with Euler would be much larger. So even though Euler evaluates f once, whereas fourth order Bronco cutout evaluates f 4 times, to get the same level of accuracy, it's no contest. The fourth order method that's more expensive per step needs fewer steps, so in efficiency, it's going to win by a long shot. Okay, so this is how these methods can be used in tandem to produce a result more efficiently. Now, it won't really be clear until next section, actually Tuesday, what the benefits of implicit methods are in terms of being able to take larger time steps. Because right now, all we can see is that implicit methods are more work per time step because you have to solve an equation. But it actually pays off. For certain problems, people wouldn't dream of using anything else. Well, okay, I do, but but that's something else. You have to think extra weird to get around that, and I think I'm up to it. Okay, so any questions about how a predictor-corrector method works? So normally done with just the steps I wrote there, so one iteration, like one fixed point iteration, but this is an option that may pay off in some cases. Okay. All right, now, so now we're going to take a look at how do we analyze the accuracy of these methods. How can we be sure that you're going to deliver a certain order of accuracy? How can we be sure that you're going to produce a viable solution at all? And that's what convergence analysis is about. Okay. Now, this is actually a long section, which is why it'll spill over into Tuesday. But there's going to be discussion of both one-step methods and multi-step methods. For today, I'm going to focus on just one-step methods. So there's 3 essential concepts for convergence analysis. The first is consistency. There is a formal definition in the text, which actually for general time-stepping methods is really cumbersome, so I'm not going to get into that here, but I think an informal definition will be more helpful. As h goes to 0, or time step goes to 0, the numerical scheme converges to the actual ODE. So your Euler's method, for example, or your fourth-order Bronco cutout method, as h goes to 0, will actually become y prime equals f of t and y. Now, more formally, the So this expression tau n of h, which is defined to be the local truncation error. And how you get the local truncation error, I will define it more rigidly for one-step and multi-step methods separately. Do it for a general typesaving method. I did it in the book, but again, cumbersome. Is what you get by you substituting the exact solution of your ODE, y of t, into the numerical method. Because the numerical method only approximates the ODE. So if you plug the exact solution of the ODE into the numerical method, it will not satisfy it exactly. There's going to be something left over. That something is called the local truncation error. So a method is consistent means that the limit as h goes to 0 of your local truncation error is 0. So that's all it means. But what you'd see is, as h goes to 0, the numerical scheme converges to the ODE. Right. And consistency is one of those things that's generally fairly straightforward to check, as I'll show you. Okay, so that's the first essential concept. The second essential concept is stability. So these also more easily defined for one-step methods and multi-step methods separately, but the general idea is that the growth in the error is bounded over time. In other words, more precisely, given numerical solutions, yn and yn tilde. So for instance, maybe they were produced by the same method, but maybe they come from different initial data. So stability means that the difference between these two solutions is less than or equal to some constant k times the difference in the initial data. And that's for all n between 0 and however many time steps you take. So you're still going up to a fixed final time, but this value here is the maximum number of time steps you can take for a given h. Now, the number of time steps could become infinite, but the point is you're still dealing with a fixed finite interval in time that you're time stepping over. So this has to be true for some k, some constant k, and a constant k must be independent of h. So when a method is unstable, that means that a small change in the solution could lead to an arbitrarily large change. A small change in initial data could lead to a very arbitrarily large change in the solutions, and that's unacceptable. So we just want to make sure that as h gets smaller and smaller, that you're taking more and more time steps, that does not lead to more and more deviation in the solutions. Okay. And for multi-step and one-step methods, there are different ways of checking stability, but each of those is fortunately not too difficult. And then what we really care about is convergence. Convergence simply means that as h goes to 0, the numerical solution converges to the exact solution. And I gave this definition before. So you look at the numerical solution at a certain time and the exact solution at the same time over all time steps that you would be taking. Okay. Then that has to go to 0 as h goes to 0. So at least we can be sure that as our time steps get smaller and smaller, we're only going to let h be so small for efficiency's sake, but at least we have this confidence that what we're getting really is an approximation of the exact solution. Now, I said convergence is the only one we really care about, but convergence is difficult to show directly. Now, I did do it for Euler's method, but Euler's method is by far the simplest time-stepping method. So for something like 4-4 Brancata, it'd be much more of a chore. However, if you, the main theoretical result that relates all of these, and some of you put that on the quiz already, is that if a method is consistent and stable, then it is convergent. This is actually the, well, actually, I was going to call it the lax equivalence theorem, but that might only apply to PDEs. Okay, well, yeah, never mind that. There are different theorems that make statements like this. Like, for instance, you say if a method is consistent, then it's convergent if and only if it is stable. So, but this is like the weakest statement I can make, but it's the most important one because that's what you're trying to do. You're trying to show a method is convergent. So what do? You show it's consistent and stable because these things are easier to check than checking for convergence directly. Like at the end of a section, I have the Dahlquist equivalence theorem makes this statement for multi-step methods specifically, but then you can see there's a similar result that would hold for one-step methods. Okay, so that's what we're going to look at is how do we show that one-step methods are consistent and stable. So we're just going to deal with one step today. Okay. Okay. So, how you check consistency and stability for a one-step method? Okay. Well, first, I'm going to describe, here's how we write down a general one-step method. Because a one-step method only uses information about solution from time tn to time tn plus 1. So, for a generic one-step method is yn plus 1 equals yn plus h, and then we have some function phi that depends on tn, yn, and h. Okay, so for okay, it occurred to me that this definition is much more readily applicable to explicit one-step methods. Otherwise, it has to include yn plus 1 in the definition of phi also.
Is that a T naught or T N?
That's a Tn.
And it's Y N too, right?
Yeah.
Okay.
Okay. Yeah, I guess my n's need a serif or something. Okay. And actually, I'm going to cheat a little bit and confirm this for implicit methods. Okay. Yes. Okay. Like, but yeah, like in the examples I'm seeing, they just deal with explicit ones, so it's kind of a cop out there. Books cop out a lot. It's one reason I wanted to write my own. Yep. Okay.
Or they tell you to do it yourself.
Oh yeah, yes. Proof left to reader. Yeah. Yeah. Okay. Well, I guess my book's kind of guilty of that. I have a lot of exercises that I did not assign, saying prove this theorem. Well, okay, maybe I assigned a couple of them.
Or we'll prove the first half of the theorem, and the second half is left as an exercise.
Oh yeah, yeah. No. Yeah, we're all bastards that way. Okay. So, yes, it's okay. So really, yeah, this was an implicit method. I have to include yn plus 1 in the definition. So this would apply for the explicit case. But I think the only homework problem I gave for this, or I could have given for this, actually deal with explicit methods. Okay, so since the issue is not going to come up for you guys, it's not going to come up for me either. Okay. So the idea is to check if a one-step method is consistent. The condition is very simple to state. That is that if you plug in h equals 0 into this function phi of t and yn that describes the one-step method, it must equal f of t and yn. Okay, so I'll show you an example of that. Okay. So the example I'll use is the midpoint method. That is yn plus 1 is equal to yn plus h f of tn plus h over 2. And then we have yn plus h over 2 f of tn yn. So this right here, this whole invocation of f, is phi of tn, yn, and h. So what you do is just go ahead and plug in h equals 0. And what will happen is that'll go away, and then all that will go away. And what's left? All you got is f. So if you plug in h equals 0, it collapses to f of t and yn. So one of the homework problems I gave is checking if the four-photo run cutter method is consistent. You plug in h equals 0 and make sure that everything that gets added onto like yn that's multiplying h, that whole thing collapses to f of t and yn. Okay. So a little more tedious than this, but not very. So not much to it to make sure it's consistent. Okay. And then, but the thing is, consistent only tells you that the error goes to 0 during a time step if h goes to 0. This doesn't tell us, for instance, if a method is first order accurate, second order accurate. So for that, we will look at local truncation error. So now I can give a more formal definition of that for one-step methods. So tau n of h is equal to y of tn plus 1, that's the exact solution, minus y of tn all over h, minus phi of tn, y of tn, and h. So what you're doing is you're plugging the exact solution into this one-step method, and you're isolating everything on one side, set it equal to 0, and then you divide through by h. That way, so the idea is h goes to 0, tau n of h will converge to, well, this is a derivative. This is y prime of tn. And this should converge to f of tn, y of tn. But that's 0, because that's y of tn is the exact solution. Okay. So local truncation error is the numerical method rewritten in such a way that it more closely resembles the differential equation. So we can show that one converges to the other. Okay. Now, for a method like this midpoint method, how do we know? This is actually a second order accurate method, but how do we know that? We actually go ahead and compute the local truncation error. And we'll reach by Taylor expansion. Yeah, I know. And see what we get is second order accurate. So how that would go, so local truncation error is equal to, we have y of tn plus 1. That's what you Taylor expand, is y of tn plus h, y prime, but that's f of tn, y of tn, plus 1/2 h squared over 2, y double prime at tn. Let's see, I need to go out one term more. H cubed over 6, y triple prime at some unknown point. I'll stop there. Minus y of tn all over h minus the phi for this method. So minus, in this case, the midpoint method, f of, and now the f part, I have to do a multivariable Taylor expansion of that. That's going to get ugly. So I have f of tn yn plus h over 2 partial f with respect to t plus h over 2 fn times partial of f with respect to y. Well, this would continue. Then I would have second partial derivatives. So with respect to t, I have h over 2 squared. Okay. Second partial with respect to t of all this is times 1/2 plus 1/2 h over 2 fn squared second partial with respect to y plus h over 2 fn partial of f, second partial with respect to t and y, and so on. I won't continue it from here. I won't need to. Now, how can all this simplify? First of all, y of tn's cancel. Here I have hf over h. Well, that cancels to just plain f. And that cancels with this f down here. So these terms cancel each other out. And y double prime is the same as a derivative of f of ty with respect to t. And this came up when deriving a Truncation method, that this term is actually going to cancel with these two. So if you look back at how, actually it was the midpoint method that derived as a Truncation method, that was worked out back then as to why those terms cancel. And I don't need to try to simplify anymore, because look at what's left. I have h cubed over 6 over h, so that's order h squared. Everything down here is order h squared. So I'm done. I've shown that the local truncation error is order h squared. This is a second order accurate method. If I were to try to analyze these terms further, I would find that they would not cancel. So second order is the best you can get from this method, but better than first. Okay, so it's an ugly exercise, definitely. That's why I only assigned a problem showing that the fourth order Truncation method is consistent, not show that it's fourth order accurate. That would make you all cry. So, no, I'm not going to ask that during the oral final either.
But if we want to show that it's fourth order accurate, we're more than welcome to.
I don't have that kind of time to sit there and check your work. Okay. I think I meant to. I'll try including it in the book, and I started working on it. I was like, no. That's how bad it is. So kudos to Rugger and Kutta for developing. All right. So any questions about what happened here as far as what could be simplified? Okay. So yeah. So checking consistency is quite straightforward. It's getting over accuracy, definitely more work. Single and multivariable Taylor expansions, but that's the process. Okay. Now, the other thing to check is stability. Now, at least there, it's a binary thing. It's yes or no. Yes, it's stable, or no, it isn't. Manipulation is not quite as nasty. And for one-step methods in particular, it's easy to state the condition for a one-step method to be stable. All right. So stability so we assume that f from our ODE is Lipschitz continuous. And it has a Lipschitz constant, Lipschitz continuous in the y variable. It doesn't have to be Lipschitz continuous in t. With a Lipschitz constant of L. So in other words, if I look at f of t y2 minus f of t y1 is less or equal to L times the difference in y values. Another way of saying it is that, for instance, it's Lipschitz continuous if partial of f with respect to y is bounded by L. So we're going to assume that because that would give us a well-posed problem. So the general one-step method written in this generic form is stable if the function phi is also Lipschitz continuous. in this variable. The y variable, I've written it as yn. Now, in the case of, for instance, Euler's method, phi is equal to f, so it's automatically stable. It just inherits a Lipschitz constant of f. But for other one-step methods, there's a bit more work to do. So I'll give you an example of showing stability for another one-step method. Where'd it go? Okay. Well, again, we'll use the midpoint method. So my generic function for a midpoint method is phi of tyh is equal to f of t plus h over 2, y plus h over 2 f of ty. So I need to show that that function is Lipschitz continuous in the okay. Oh, I should need to emphasize the Lipschitz constant, which I'll call LV, must be independent of h, at least for h sufficiently small. So in other words, you can't have a situation where if h is going to 0, the Lipschitz constant grows. That's not allowed. Okay, it's one of those finer technical points that everybody forgets. Okay, all right. So how do I show that this is Lipschitz continuous? Using the fact that f is Lipschitz continuous. So I can say that phi of ty2h minus phi of ty1h. So I go ahead and write all that out in terms of f. So that would be f of t plus h over 2, y2 plus h over 2, f of ty2. And then I have the same expression with y1. Okay. So what I have here is a difference of f values. So what I do is I use the fact that f is Lipschitz continuous. Say this is less than or equal to L times the difference in y values. So I just take the y values from here. The second argument is y2 plus h over 2f minus y1 minus h over 2f with y1 plugged in. Okay. Now, here I have y2 minus y1, and then I have plus h over 2 times the difference in f values. So I'll finish it over here. So I'll go ahead and rewrite that so it's easier to see what's going on. Okay. Yep, almost done. All right. So let's just rearrange the terms in that. So we have y2 minus y1 plus h over 2 f ty2 minus f of ty1. Okay. Now, triangle equality, I'll break these absolute values, break these terms up. All right. Now, this is, again, a difference of y values. So I use the fact that f is Lipschitz continuous again. So now I'm going to get L y2 minus y1 plus h over 2L y2 minus y1. And now what I can do is factor, I can factor y2 minus y1 out to the right. Oh, sorry, this should be L squared, because L here and L here. Okay. So now I've shown that phi is Lipschitz continuous with this Lipschitz constant. So this is what I call L phi. So what I can do is if I assume that h is sufficiently small, I assume that h is less than or equal to some value h naught, then I can say that my Lipschitz constant L phi is less than or equal to L plus h naught over 2 L squared. So in other words, if h is sufficiently small, then phi is Lipschitz continuous with a Lipschitz constant that is independent of h, because notice there's no h in here, only h naught, which is a fixed constant. So the point is Lipschitz constant is not growing as h goes to 0. Well, actually, it's shrinking. It converges to L. So I can conclude from that that the midpoint method is stable. And earlier showed it was consistent. So we can conclude from those two things that that the midpoint method is also convergent. So for one-step methods, using the same approach that I used some time ago for Euler's method, that exact same argument can be used to show that if you have a general one-step method that is consistent and stable, you can also show that it's convergent. Also, whatever order of accuracy the local truncation error is the order of accuracy for the global order of accuracy. Because what we really care about is not how much error is committed during one time step, but how much error is accumulated over all time steps. But if you have a one-step method that is second order accurate, locally, and it's stable, then it's also second order accurate globally. So there's no distinction between the order of accuracies in that case. So generally people just show what the local error is, show that it's stable, and then that's the end of it. Okay, so this is how we analyze the convergence of a one-step method. So make sure that phi converges goes to f as you plug in h equals 0. Make sure it's consistent. Show phi is Lipschitz continuous to show that it's stable. From there, you know it's convergent. It's done. So what I'll do on Tuesday is show a different procedure for analyzing the convergence of multi-step methods. Actually, yeah, but it's going to be more of a pain. But okay, so any questions? Oh, we're almost to the end, so one thing to be happy about, I guess. But, okay.